I'm Jewell, Principal Software Engineer on Azure Sphere for the security side of the system. I'm responsible for the security from the hardware chip all the way up through user land. First few slides for marketing style. Marketing team kind of threw them at me and said, here's slides to start with. Everything else I had to build off of. So, see where things go. Security is foundational. It must be from the beginning. That's obviously from all the talks here. It's hard to actually get security if you don't build in from the start. Case in point, the Rari botnet back in, I think it's 2016, affected 100,000 devices. It's still being dealt with even today. There's no way for the devices to be remotely updated. It's using attacks that allow it to easily propagate on a bunch of IoT devices. Another case, an example, is hackers will get into a casino through a thermometer. I highly doubt the thermometer has any form of firmware update or any way to even fix the problems that were abused to get into a casino. And that was in 2017. And even this year, there was a core TCP flaw in a real-time operating system that exposed 200 million devices. These are devices that, for the most part, most of them have no way of updating. None of them have ways to be corrected and fixed, yet they're being used for IoT. They're being used for things that need to have constant communication. There should be some way to deal with this. One of the things that Microsoft put together is 7 properties we've identified as things that a highly secure device should have. A hardware root of trust that's built into the hardware itself. Some small of trust. The trust computing base is actually quite small, so you can actually trust it. There's multiple layers of defense in the system itself, so if you have one level of defense fail, you still have protection. Able to enforce actual hardware barriers between different parts of the system. Lots of parts of computers nowadays, especially IoT devices, you have one chip. You have one thing that if it fails, you have control of the whole system. Able to have certificate-based authentication. We use this constantly for TLS. We use this constantly on the web. Yet IoT devices are not making use of it. And of course, when there is a problem, being able to detect the error and report it, along with being able to update and renew security so you know things are actually good. The problem is for a vendor to actually implement all this, it's not easy. This requires time. This requires figuring out a proper design. This is not an easy thing to accomplish. And a lot of IoT devices are being more and more global scaled. Being able to actually expect a vendor to go out and implement a whole global scale system to update all their devices is not an easy task. So the Azure Sphere processor, the Azure Sphere chip geared for IoT devices is supposed to be for a hardware certification where you know that the operating system's trusted and secured, allowed for validation with the cloud, which then allows for validation of the hardware itself. You have a constant loop of validating each other. So the rest of the talk is actually getting into each of our sections of modules. And the Azure Sphere actually exists nowadays. There's actually you actually go get dev boards right now using this actual processor and chip. This isn't a pie in the sky, we hope to do this one day. This actually exists now. Overall, we have the hardware itself with our security design. We have our security monitor that runs on the system. On top of that is a Linux kernel, so we're actually making use of open source and its actual secure infrastructure. Then we have our internal core services for communicating with the cloud and allowing for updates from remotely while also doing system validation. And then you have the cloud services that provide the back end for actually validating and protecting all this and allowing for the updates. And this is our hardware. So in one actual processor, we actually have 5 different internal processors. We have a Pluton security processor running an ARM M4 chip. We have a Cortex A chip for the Linux and security monitor. We have 2 Cortex M4s dedicated to direct I/O access. This allows for any form of IoT device that requires immediate I/O access so that you can't get fast enough through the Linux kernel. You can actually run separate on the M4. And also provided is the actual network chip itself. So we actually can provide Wi-Fi embedded in the chip. And the flash memory and the onboard memory are not mistypes. We only have 4 megs of memory of flash and 4 megs of actual physical memory. So we're actually running Linux userland with 4 megs of memory, 2 for the kernel and 2 for userland. On top of that, we have the hardware firewall. The hardware firewall gives us immediate control as to what chip can talk to what. So we can guarantee that the Cortex M4, even if there is a way to abuse it, can never actually talk to the network chip. It can only talk to the Cortex A7 through the communication path we opened up for it. Part of our defense in depth, part of our actual security is the hardware firewall. It's configurable, but its configuration can only be done through Pluton. It can only be done through a security monitor also. Once we actually set up the rules that we want, we can lock them down. Once those locks enable, even the most trusted chip on the system cannot modify the firewall. So even if you have a way to abuse one of the chips and gain access to the chip, you can't use it to bounce to someone else because you can't modify the firewall to open up more paths of attack. A lot of systems nowadays don't have a way to mitigate attack vectors, so as soon as you get control of one chip, you can start poking other registers and other parts of memory and get access to other parts of the system. And here, we purposely decided that even our most trusted chip cannot reset the firewall once we lock it down. That moves into our secure processor Pluton and secure world. Pluton runs on a dedicated M4. It is the first chip to come on. Everything else is turned off. It controls actual system boot. It goes through and does its validation of secure world and gets things up and going. The public and private keys are not accessible to, the private keys on the system are not accessible to Pluton. Our most secure chip cannot talk to and access the actual private keys on the hardware. So when a new chip's made, during the manufacturing process, it's validated and tested. During that validation and testing, there's no public or private keys. Once the manufacturing turns it into secure mode, and that's at the actual plant itself, the private keys are generated internally in the hardware, and the public key is securely transmitted over to the cloud. We now have a way to guarantee a public key for a device with no way of knowing what the private key is. We can only ask the hardware to go validate or sign stuff for us with no way to actually leak the key out. It's embedded in the actual hardware. Any of the flash memory writes, any of the flash modifications, has to go through our secure chip. The A7 has no access to the flash. It has to go through Pluton. Because we have security keys and various authentications, security monitor is able to validate the Linux kernel as the image that we want. That has not been modified. And any application running on the device is verified by a security monitor in Pluton. So although we have a Linux application, the Linux kernel is not the one doing the validation. It's being passed up to the secure area for validation of the actual data that's sitting on the flash before actual execution. We pull our kernel straight from kernel.org. We have a bunch of patches that are already available to the public that we do for the kernel itself. We have our own custom LSM. Because we only have 2 megs of memory for the kernel, again, we only have 4 megs of memory total, we don't have room for SE Linux. We don't have room for seccomp and a bunch of other protections that normal systems rely on. So we decided to go the minimal route. We don't support modules. We don't allow for runtime code generation for any of the firewall rules. We even remove sudo. We don't need applications changing user IDs. Every application runs as a unique ID. They have no reason to change IDs, so why even have it in the kernel? We completely removed it. This adds a layer of security because now you can't move from one ID to another unless you're actually breaking the kernel itself. We went as far as disabling memory page executions. So if you ever write to a memory page, there's no internal bit that gets set. So even if you say the page is read-only and you want to make it writable in the future, it's still not allowed. It was made writable in the past. This complicates a lot of attacks. This limits what attack vectors you actually have on the system, too. We have no use of a shell. We plan to run user applications that are created by a vendor, created by a customer that's putting out a bunch of IoT devices. Those devices don't need a shell. They have no use of a shell. That's a security hole, potentially. At the same time, we're leveraging open source software. Why? Because it's been tested. It's being used in the public. People are finding constant flaws and not relying on our own internal team and not relying on some other group at Microsoft to go do validation of a custom written library. SSL is hard. People keep finding bugs with OpenSSL, as an example. So why not make use of what the open source software has already done for the system? As I said earlier, each application is isolated. Each application runs as a different user. This actually makes easy use of what Linux already gives us, which is user isolation and control of what applications can access. Because of our limited space, we have a custom init program. We don't have the default init you find on different Linux distributions. And it doesn't even run as root. The only thing it runs as root is the kernel threads. Part of our build system is using this GCC compiler. And this is part of our SDK that gets released when people write software for it. It forces people to, by default, have security built into it. Turn on the defaults for ASLR. Turn on the defaults for stack protection. This allows for easy ways to add security to a system without having to do a whole lot of work. Give someone an SDK to create an application, and it automatically puts functionality in for them. We modified the Linux network firewall. We can actually, so right now, on a normal PC, if you have a firewall rule for gain access to a certain domain or a certain IP, it tends to be accessible to every application. Well, we decided that we wanted to make it more tight, or tightly controlled. So the network firewall rules are application specific. If application 1 wants access to an IP, it does not mean the second application has access to it. And because we control the DNS lookups, we can easily put into the application manifest what domains an application is allowed to access. So maybe an application has example.com in its manifest, which is built into and the signed image. DNS looks up and sees the proper IP. Firewall rule is set for that. Another application it cannot access other domains. It can't access other things unless the DNS itself gives a different IP. And we default deny all traffic. This gets into the cloud services. How do you validate the device itself? Well, we have attestation, which is modified and verified based on different hashes of different core components. But a lot of attestation out there is easily fakeable. You can easily modify the attestation values. Well, our attestation is actually handled by the hardware chip, which means you can't write to the register directly. You can only do updates to it. Any of your updates modifies it in a way that's effectively a new hash of it. So if you want to reset it, you have to start over with a full reboot. Well, because we have the attestation value, because we have a private key that we only have the public version of, because the hardware has the actual private key, we can ask the hardware to go sign the nuance with the attestation value and give us the result. Now we can actually validate the actual hardware itself is something that we want. And actually is a device that we actually know. This makes it harder to clone devices, makes it harder to fake a device. It also allows us to know if old software is running because the attestation value is going to be the wrong value that we want if it's not the current version. If everything passes, we can give it a certificate for communicating with the rest of the cloud or a certificate that can be used by the vendor for their own internal systems if they want something more secure than their own stuff. This also allows for daily check-ins because it's only 24-hour authentication. So daily check-ins allows for monitoring critical security while also allowing for system updates outside what the vendor has. So even if the vendor is not modifying their application and not providing new versions of their software, we can still provide updates and security to the actual core systems components and to the core operating system. For many years ahead of what the vendor itself allows. How many IoT cameras out there, how many different IoT hubs out there, once they get released to the field, have no firmware changes, have no updates? Problem happens with the operating system, problem happens with the software, there's no updates for it. We can at least keep the core system secure and hopefully have enough layers of protection that even if the application the vendor wrote is buggy, we can help protect the system to some manner so that it can't easily be abused. Going back to the botnet, that was effectively bouncing around across different devices. Well, if we can make sure that the network's never able to access other IPs, this makes it hard for a device to even become part of a botnet. One thing that a lot of people don't talk about, though, is all this is great and wonderful. How do you actually keep up to date on all this work? This is back to what a lot of people are expecting vendors to go through and put the effort into. We are putting the effort into it, into the build system itself. This is what it takes to keep our system up and going every single day in every single update that we have. We use the Yocto build framework to actually get our core system going. We have automated tests, both static code analysis and fuzzing. And we do actual functionality tests with both emulation and on the actual hardware. So a simple code change anywhere in the system requires all of those to pass just to get the code changed into the system itself and approved. On top of that, we check CVEs daily. We have an automated script that tells us of any CVE for any open source component that we're using, including the Linux kernel. We did 48 patches in 2019, and we bumped 6 different components for their versions outside of what Yocto is giving us. The recent Linux TCP stack panic that happened. We had that pushed out within 2 days of the kernel patches coming to public release. On top of that, our nightly builds check security flags across all components. There's a check-sec program that's open source. It goes through and validates things like ASLR and stack protections and a bunch of other simple stuff on your binaries. We've taken that approach and expanded it to a bunch of other functionality for validating modules and validating that different parts of the system are doing what they're supposed to have outside of we have simple protections turned on. We even went as far as being C++ 17 compliant. Most of our internal code is actually written in C++. This includes the boot code. This includes our secure code. So security minor is even in C++. And people look at us strangely. It's like, why don't you want that in assembly or in pure C? Well, this actually gives us the benefit of the modules that already have buffer validations and array validations, making it harder to actually access outside of what you need. So it's actually providing a lot of protections in that manner. It's not easy to expect a vendor to go through all this effort trying to protect a simple IoT device. This is why a lot of IoT devices nowadays are insecure. It's too hard for a vendor, it takes too much work, it costs too much money for their dev team to go through, write a piece of software and make sure everything's good for years to come. Our goal is to actually have a system that, here's a chip, you can write code for it, we'll take care of the security as best as we can, even if you're not keeping up to date on the actual versions and keeping track of all the CVEs or any other components that you might be using that are secure, insecure, or flawed, or its flaws come across in the future. Any questions? Any curiosities? I try to go through things a little quick because of everything being so behind on time. Keep in mind, I've only been here since February, so I may not have answers to everything.
So you mentioned QEMU, or at least in that picture, functional testing QEMU. Does that mean that you have effectively the Azure Sphere in QEMU, as in the full emulation of it?
The full chip is in QEMU, and so we actually have a QEMU system that allows us to boot our Azure Sphere chip from the secure processor all the way through all the others.
Is it going to be upstreamed? Is it upstreamed? I mean, is it upstream QEMU, or is it only in your own private branch?
I don't have an answer for that. I don't know.
Okay. I have one more question, if that's okay. You mentioned the hardware firewalls. Can you actually expand on that one a bit more, or no?
So in the actual hardware itself, and I'll expand as far as I can based on my knowledge, not because I can't go so far. The core chip has multiple different actual processors in it. All of those go through an individual firewall, allowing us to control which actual connections can be turned on and off between the chips for communication. Okay. So we can actually shut off or turn on certain communications. By default, they're all off. So no one can talk to anyone until the secure processor starts turning on certain ones in a certain order and specifies the order. So that's why, like, the Wi-Fi chip only has access to the A7 because that's where the Linux kernel is, and they need to talk to each other. It's isolated from everything else. It physically cannot talk to anything else from the hardware firewall.
Hey, so I had a question on the private key generation.
Yes.
You said that that is burnt into the eFuses in the beginning. So is that done during the manufacturing process?
Yep. So during manufacturing, the system itself is in a unknown or testing state. During manufacturing, once actual chips are tested for being good, the chip itself is moved to a secure state. At that point, it's generated internally in the hardware. You can't move back. You can move forward a state, but that forward state is the end of life. Chip is useless. You're not going to do anything with it because everything's gone.
Cool. That sounds like a pretty good design. Also, I had one other question on the firewall separation. You said there was modifications to the kernel for each program to have individual firewall capabilities.
So the Linux firewall, we tie the user ID to the firewall rules. So when so by default, you can't have anything come in. If something's trying to access out, we can check the user ID for the firewall rule itself and see if we have anything allowed before actually allowing the connection out.
Awesome, thank you.
So go ahead.
Oh, just very quick question. So maybe I missed it, but what is the status of the project when it comes to the source code? Is it available any place? Because I Googled and couldn't find it.
There is a area for Microsoft for various releases that we've had, which allows you to get all of the kernel modifications and our Yocto build stuff. Our internal services are on the device itself. We don't currently have out in the public, well, not in the source code form. We have had various patches and various things that we have shoved or did pull requests against to other modules. Example, muscle, we have actually offered different changes that we've done to it.
Quick question, going back to some of the things that we were talking about this morning. If you wanted to, or if I, as a consumer of this, wanted to extend, maybe it's the attestation stuff that you talked about, but basically I wanted to be able to extract some information about the configuration of the hardware and possibly what firmware is there, maybe properties about that firmware. Is there a way to extend what you have in here with additional telemetry information that you could be bringing back off of the device back to the cloud so that it could be analyzed?
I know there's our telemetry. I also know that there is telemetry that customers can send back. I don't know much more than that, though.
Is Flash encrypted on these devices? I'm thinking about a scenario where, let's say, somebody steals one and wants to get secrets off of it that may be useful for interacting with maybe a web API or something like that. You mentioned a 24-hour long certificate. Is that what people should be using instead to talk to web APIs? Or if they had other secrets on there, would those be liftable and unsealable?
So we have a form called Secure Flash. So the current dev boards do not have the Flash encrypted by default because we actually have Flash for most of the data. However, we do have Secure Flash storage for data storage on the device. I don't know the current state of the Secure Flash storage or what is going on in the future for full Flash protection. Again, the current boards are the dev boards because we're still going through the process of beta and getting this fully done.
Okay, so earlier you mentioned the private key is generated, and sorry, I'm over here.
Yep. Okay.
Private key pair is generated. Is it generated on the chip or externally at manufacturing?
On the chip, which is why Pluton has no access to it.
So how do you guarantee randomness or enough randomness in the generation of the key?
I don't know enough about the hardware randomization itself. I do know that the hardware randomization modules that it came from are supposed to be used for, because it's part of a security chip itself. So they're supposed to be for actual hardware randomization data.
Okay, so you have dedicated hardware that randomizes it.
Yeah.
Okay.
So dedicated hardware security has not only the various encryption for public-private key and AES and a few other encryption modes, it also has a dedicated random number generator that's in hardware.
Architecturally, you're talking about like the flash rate security being controlled by the the embedded Cortex M there. I was just sort of curious, like how those were designed to expose the risk of having a sort of hidden secure domain with access to all of your secrets that you can't really inspect from the main Cortex A very well. Like you have a deputy that's parsing something and checking like ranges for making sure that you're in bounds. So it seems like you do have some attack surface. I'm just wondering, like, is the Cortex M then protected so that even if you compromise it, you can't then access secrets directly from that domain?
The secrets embedded into the hardware itself is inaccessible from the Cortex M. Example, the private key. The boot ROM itself that actually gets the Cortex M up and going for Pluton is extremely small, somewhere around the neighborhood of 16K or so. This allows us to guarantee that at minimum we have the ability to even update devices if we find a flaw in, say, Pluton or security monitor, compared to those being fully locked off and never modifiable too.
I'm here. The pre-checks you do for each pull request is super impressive, including the fuzzing stuff and secure analysis, static analysis, and running it on real hardware. What's the turnaround time for that? So how long do I have to wait for the green check mark to appear?
The build system is under an hour.
Okay. And how do you do you run this fuzzing step?
Depends on what parts of the system are being modified.
Okay.
So if I'm making modifications to a file parser, it's different than modifications to the network handler.
Okay, there's some policy in place that sees, okay, these parts about to change, so I run that fuzzing job. So, And another short question. The hardware tests you run, are this all automated? So do you have a system that flashes real hardware, reboots it,
Yep, so
checks
we
if it comes
have
up?
a number of actual hardware devices just sitting there waiting to run tests. And then we will grab one of the devices, shove down the compiled build image, and automatically run through all the tests that we've created. And we continue to expand tests daily. So more and more tests show up daily as to how many. I don't remember how many we're up to. We're in the thousands right now for different hardware tests it goes through.
Okay, thank you.
So just to make sure I understand the scope of this part is intended to be a sort of system as a whole for IoT devices, right? It's not intended to be a security chip partnered with additional separate general purpose processing.
Yep. The goal is a system as a whole, knowing that it's so hard to keep the whole system secure so that vendors can worry about actual functionality and code they need and not have to worry about the whole system.
Sure. Okay, thank you.
Do any of the processors, even though you have a firewall, do they have access to the cryptographic operations of the security chip?
Pluton's the only one that can make requests to the actual security chip to do things, but it's a send command into a black box for hardware chip and get output.
So I could send in known requests for encryption and get answers out?
Only if you're Pluton. So if you're only the M4 secure chip, yes. If you're the A7 from Linux, no.
Let's see. Is this provided as a system on chip, or is this a set of components?
System on a chip. All those are in one processor.
Is the RAM shared between the components as well? Essentially, how many memory controllers are there?
Parts of the RAM are shared, mainly due to Secure World and Linux running on the same processor. They both run on the A7. Pluton has its own internal memory to handle and deal with stuff.
Awesome, thank you.
So what's Microsoft's core goal here with the making of the chip? Is the intention, we made a chip, we like the architecture, dear everyone who makes a board, use exactly this one chip? Or is it, we made a chip, we like the architecture, dear other chip makers, please adopt the same architecture? So like what level of competition are you expecting between different chip makers versus just everyone use our chip if you want to use Azure?
Our current chip maker is MediaTek. NXP's already said they're going to be making an Azure chip also, or Azure Sphere chip. We're working with them for final design of what that would look like.
Okay, so it sounds like then any chip maker could come to you and say like, oh, well, I like your architecture. Please, give me all the design docs and I want to build a chip like that.
Yeah, and we work with them for what the final design looks like. So it's not just someone stamping Azure Sphere on a chip without our looking to make sure that we actually approve of the final design and final interactions because of things like the hardware firewall and other parts in the actual hardware itself.
All right. We also have 2 talks on Thursday. One's from ARM on what seems to be a slightly more general version of this called Corestone 700, and then some research from Sherry, which might have inspired some of the hardware firewall pieces. We should probably move on. This is a great topic, but thank you very much.